Hi, if you are here, probably you have seen my poster in the European Fuel Cell Forum in Lucerne. I am Álvaro Rodríguez, and please, be welcome to this presentation where I will explain you a little bit more about our work regarding this topic, the detailed numerical simulation of the performance of the functional layer of solid oxide electrolysis cathodes. Let's start. As you probably know, solid oxide electrolysis is in a pre-commercial stage that has still to face challenges to reach the market, like scalability or degradation phenomena. That's why in this work we are aiming to study the behavior of the electrolysis cell not only from a macroscale point of view, but also from a microscale, where the complex electrochemical phenomena take place. Simulation tools can pave the way to the commercialization by providing us a useful insight into the coupled multiphysics phenomena taking place in the porous electrodes. However, current macroscale CFD models used to include some fitting parameters that are not realistic and do not consider the real material properties of the microstructure of the cathodes. That's why in this work we have proposed a multi-scale methodology in which we are developing some mesoscale and microscale models in order to analyze the influence of the material in the final behavior of the cell or of the stack. In this particular case, I am focusing on the first step of this multi-scale approach, which consists of three main parts. Now, I am going to talk about the numerical reconstruction, and I am going to briefly explain the three different steps that we are considering. First, we are simulating the powder compaction of the nickel and the yttria particles. We are performing this part with lights, which is an open source code for the discrete element method. After that, with the output of this module, we are performing the sintering process, in which these particles are joining together to form this final sinter microstructure. Finally, we are also performing the reduction of the nickel oxide. Nickel oxide particles reduce to metallic nickel when it is exposed into a hydrogen atmosphere. This step is a very relevant step as the final porosity of this porous media is driven by this reduction. Finally, with these three steps, we are obtaining the final porous media, which is the input of the next section, the numerical characterization. As I was explaining, once we have this synthetic microstructure, we are going to analyze it with two different approaches. First of all, we are using Python scripting in order to calculate different topological properties of the microstructure as the specific area, the pore mean diameter, or the density of the triple phase boundary. We are also performing some CFD simulations with OpenFOAM, which is an open source code for fluid dynamic simulations. With these leader models, we are able to calculate different physicochemical properties as the permeability, the thermal, electric, and ionic conductivities, and the reaction rate. That is the variable in which we are focusing on this particular work. Then, I am going to explain how we calculate this reaction rate. Regarding the mathematical model, we have two different models. One for the fluid phase, where we are considering mass, momentum, and species conservation, and another one for the solid phase, where we are considering electrochemistry phenomena and ion and electron conservation. As you can see in this image in the upper part, when talking about the solid phase, we are able to study and to identify two different phases, the nickel and the yttria phase. And we are also able to identify these triple phase boundary points, which are the points in which the reaction is taking place. As I said before, we are considering models for both fluid and solid phases, and these models are coupled. That means that the fluid results are mapped to the solid phase, and the ones from the solid are mapped to the fluid. Finally, as you can see in this image below, we have a numerical mesh for the solid and the fluid. Regarding the relevant boundary conditions of the model, as we are considering the functional layer of the electrode, the bottom phase is the interface between the cathode and the electrolyte, and the top phase is the interface between the cathode and the functional layer of the cathode. All other phases are considered as symmetry phases. And finally, in order to illustrate the application of this methodology, I am going to show you the results of a reference case in which we use a particle diameter of 1.5 micrometers and a nickel-yttria relationship 50-50. The images on the left show, for example, the results of the fluid phase, where you can see the hydrogen and the water mass fraction. In this case, as we are simulating this electrode in electrolysis mode, the hydrogen is being produced and the water is being consumed. You can also see, for example, the pressure drop along the electrode and the velocity path lines. On the other hand, for the solid phase, we have the electric and the ionic potentials, where, for example, we can identify isolated nickel and yttria phases. We have also the electric and the ionic current densities inside this microstructure. In this case, it can be seen that the electric current, the electrons, are going through the microstructure from the top to the reaction points, and the ionic current is being generated in these triple phase boundary points, and this current is going to the electrolyte. This methodology allows us to study and analyze how different fabrication process and how different fabrication parameters affect the final reaction rate of the electrode. So you can see here that, for example, for different input parameters of the fabrication process, we are obtaining different microstructures that we have synthetically reconstructed, and then with this porous media, we are able to characterize them in order to obtain the reaction rate of this porous media, of this microstructure. In this way, we can see how different input parameters affect the final reaction rate of our model. And well, finally, as a result, if we apply this methodology to a full design of experiments, it can help us to identify the optimal parameters that allow to maximize this reaction rate, for example. And just to conclude, as further steps, well, the main objective of this methodology is to embed these microscale and mesoscale models that we have developed in a final macroscale model. So at the end, this functional layer of the cathode will be represented by the porous media that we have synthetically generated and characterized. So that's all from my side. Thank you very much for your attention, and please do not hesitate to contact us. Thank you.